So yeah, thank you for inviting me to St. Petersburg. It's a wonderful city. I really enjoyed. So I'll be talking a bit about data compression. First of all, I would like everybody to raise their hands. And if your company has less than a gigabyte of data stored, take down your hand. 10 gigabytes, 100 gigabytes, less than a terabyte, 10 terabytes, 100 terabytes. Okay, we got some heavy lifters over there. So, well, the reason I asked is, of course, most of us have to deal with a lot of data. And one of the things that I like to look at is how we can make that more efficient. It's been just a hobby interest for me for a lot of years, but the hobby has sort of grown into its own thing. So I'll be talking a bit about data compression, what it is, and also I'll talk about how to benchmark different compression algorithms, a bit on which formats are available for Go, and also some overall recommendations to look at. So yeah, I made up this nice little quote: compression is equal art and science. It's not a finite thing, so it's not a solved space. It's something that involves a bit of creativity, which is also why I kind of like it, to work with it. So let's dive into the very, very basics. Some of you may have heard about LC77 in university or just encountered it at different places. It's pretty much the basis of most compression algorithms nowadays. Basically, it takes your input and it tries to find matches as it goes along from the previous input you sent. Try to instead of storing the things that it matches, it stores references back in history. So typically, this can be compressed a bit better afterwards with other algorithms. But there's some, like Snappy LC4 and now S2, that only does this type of compression. And that can be important for you to know when you are looking for a compression algorithm for whatever data you're storing, that this is what's going on. But yeah, it's pretty much used in every type of compression. Let's take a look at C standard, for example, how it compresses input. So it divides your input into blocks. Each blocks then have a number of sequences. It has some literals and the sequences themselves. So every entry in the sequence basically tells us, okay, copy these number of bytes from the literals, then copy something from history, then you specify how far back is it and how many bytes to copy. And then you just basically keep going. So this is it. Quite simple. Add the literals, copy from history. If there's more to go, then just do that. Keep going until you reach the end of the stream or whatever. So yeah, that's pretty much it. There was my water. So let's look at how we generate this input. How do we figure out how to compress it? So when we're compressing stuff, we take the input we're looking at, we calculate a hash. It can be different length. It can be 4 to 8 bytes typically. We see when did we last encounter this hash, and then we check, is it actually the correct value, because the hash may collide with something else. If it doesn't match, then we have some options, but mainly we just move on. Okay, let's try the next byte and see if these bytes then match. If we find a match, then we try to extend it as long as possible. So we take whatever we found in our history and we basically compare byte by byte. And as long as they match, hey, we know how that we don't have to store these separately. So yeah, and when we're done, maybe we calculate some hashes of these stuff that are actually matching, so other stuff can find that. Depends a bit on the implementation. But yeah, that's pretty much what LC4, Snappy, and S2 do. So the hash table, actually, it's quite a low-quality hash table. So the example here, we have 15 bits, which means 32K different outcomes. For each entry in the hash table, we store when did we see it in the history, and what was the actual value. We store the actual value, even though we can look it up, because then we don't only have to do one lookup to check if it actually matches. Then we don't have to check the history. So yeah, that's basically, we try to keep it as small as possible, and we accept that it's not perfect. If it was perfect, it would take up a lot of memory, and it would just be really, really slow. So hashing itself is also not perfect. It's made to be really, really, really fast. So we put in a value u and a hash length h, and basically we just multiply the input value by some value, and we take the topmost part of it and use that as our hash. It's not perfect by any means. It's not super well distributed or anything, but it's really, really, really fast. Yes. Good. So one of the things that is very common to do is to have two hash tables, which is something I first saw in C standard. It has a long hash table with hashes of up to 7 bytes at the time, so it's able to find quite long matches, but it also has a shorter one. I think this is 4 or 5 bytes, I can't actually remember. But basically, it allows you to do stuff, so we run through our input. We check, is there a long match? Can we find a long match for this? If we can, hey, let's just use the longest match we can find. Then we check, okay, I couldn't find a long match. Can I then find a small match of 4 bytes or something like that? If we can do that, then we actually check, okay, if we move on 1 byte, would we get a long match then? Because we really, really want long matches, right? If we find a long match, we use that. If we can't, okay, we'll have to use the short one we can do. But yeah, this can be extended, tweaked in different ways. But that's a typical setup of a double hash table. Of course, every time you calculate it, you also insert the new value, so you update the hash table with a new match. But yeah, that's pretty much what's going on here. So a really, really neat little thing that's it's not a standard feature of LC77 is to use repeat offsets. Here I have an example where we have some input that we are currently compressing, and we have found a match back in history that's almost the same. It's atomic weight and a different number, and then another number there. So this would actually, with repeat codes, be encoded as, hey, copy bytes from the match I found, insert the 72 instead of the 78, then copy 31 bytes at the same offset, because it's moving along, and output the new value 32, and then go back and copy from the previous offset. This enables us we don't have to specify the offset, because the compressor knows, hey, this is where the offset I was at the last position, and it's quite effective for machine-generated data. JSON is very effective at. This is XML, obviously, also binary data, because typically, you have these with small variations, but a lot of the same data that you can reuse. Finally, a neat little trick is something I also picked up from C standard. It's a really nice little thing. When we have these quite bad hash tables that are really unreliable and have collisions all the time. Sometimes we get a bit into an actual match before we find the match we're actually looking for. So instead of just, let's say, here we had the position MIC, this is the match we found. Because of bad hash tables and whatever, or we didn't hash the value initially, then we go in and check backwards. Okay, can I actually dump some of the stuff I was gonna spit out in the previous literal section? And then, hey, yeah, there's actually some stuff that matches. So that can compensate a lot for the very small hash tables. And that's a really neat little trick that I found. Good. So that's LC77. Now we move on to something completely different. It's still about compression, but it's a separate type of compressors that are called entropy coders. And it operates on a completely different level. So it's a group of algorithms that basically does the same thing. It converts symbols, which are, in case of text, is each letter or whatever you put into it. It could be pixels if it's images, and converts that into a simpler representation, a smaller representation. So yeah, there's a theoretical limit to how much you can compress it. How many bits do you need to represent a given distribution of inputs? But I'll try to visualize this with a nice picture of Rob Pike from, well, 9 years ago, I guess. So we have the picture, we have the actual values of the pixels as a distribution. So we got a lot of black, and you have for each gray value, you have a different column on there. So we can see it's 64K. It has 255 symbols. The theoretical limit for an entropy coder is about 56K, and then two different algorithms will print the actual size of it. And yeah, there's if you just represent it as 8 bits, it's of course the original size. So one thing about entropy coding is that the order of the input doesn't matter whatsoever. So here I've taken the same pictures, just moved the pixels randomly around. Trust me, it is the same picture. As you can see, the distribution of the symbols is exactly the same, but it's obviously in a completely different order. The size is pretty much also the same. You can see it's still 56K as the theoretical limit, and you have some almost the same numbers. I think for Huffman it's actually the same. So what matters then? Well, the order of the symbols also doesn't matter. So here have the same picture, but where the pixel values has been sorted by most to least. So it's basically sorting the histogram and moving the pixels. So you can see the theoretical limit is still the same. The compression is pretty much the same still. So one way of improving compression is to reduce the number of symbols. So this is in 64 colors. You can see the theoretical limit has now dropped to 40K, and the compression pretty much follows that. We can go even further, reduce it to 8 colors. You can see now the limit is 13K-ish. The compression is pretty much to that. And you can do some transformations on this. So this is taking the difference to each pixel as it moves across and down. And you can see now it's from 56K to 33K, but we can actually reconstruct it because this is a lossless transformation. But because we push the distribution to each end, we can actually compress it a bit better because we have, well, fewer symbols to do that. We can, of course, combine it. So this is pretty much the best we can do. Well, it doesn't look like that good, right? But it's pretty small. It's about 5K with at least with what's called FSE. We'll get back to what it is. But we can actually compress this quite okay. So Huffman, some of you may know it. It's basically assigning a bit sequence to your input. So I made this really artsy-fartsy thing where I assigned 0 to L, 1 0 to A, and 1 1 to R, and basically as you traverse the tree, you can, for each input, you can see, okay, this is what I should spit out. So this is a very simple way of doing it, but Huffman is used very widely today still. So yeah, the main downside is that you need at least 1 bit to represent any input, which is also why when we had this very skewed distribution, the Huffman compression actually couldn't get below an 8 to 1 because you need 1 bit to represent 1 byte as input. Then some people are doing magic. Actually, there has been techniques that gets around this limit. It hasn't been really practical because it's been quite slow. But a guy called Jarek has made it so it's actually usable nowadays. He wrote a paper on asymmetric numerical systems, and it has been transformed into several different compression algorithms. One of them is finite state entropy, and it allows us to make this limit. Basically, it creates a state table where you can represent your values. So I'll not go into too much details with this, but basically we have a distribution of the input, and we try to create a state table we can jump around in and actually represent our input. It's very fascinating, and if you like nice math stuff, there's a lot to go into. So, but for this talk, I'll skip the details. It's beautiful, but but I could talk about that for a very long time. So yeah, that's 2 of the things, the techniques we can use to compress data. There's other stuff, so things like having a shared dictionary when you start compressing. So if you have an HTML input, if you have a dictionary with all the HTML tags, so you can reference that when you start compressing, that is a way of doing it. It's fast and nice, but also a bit tedious because of course, when you send something, the receiver needs to know this pre-shared starting state. But it does work in some scenarios. You can transform the input just as we did by changing doing the difference, doing a transformation where we can revert when we uncompress. That is something that is commonly done. Finally, there's something called context mixing, which it has a lot of different states, and then you hook up either some logic that chooses between these different states, and each state can output the input it wants to get back get back the data you're sending in. It's quite slow, but that is actually where you get the biggest compression ratios today. It's not really useful in any practical sense, I feel, but maybe 10 or 20 years, who knows? So yeah, benchmarking. That's that's where we get back to the real world, right? So first of all, always use real data for benchmarking, because when you evaluate what to choose, it depends a lot on what data you're sending it, which is actually the best. So test on multiple types. Make sure you aren't testing the garbage collector. That's very easy to do because you have to send in a lot of data. You're getting a lot of data back. So make sure that you, however the compression algorithm you're using, it usually supplies some method of doing compression without and decompression without allocating stuff. So be sure to check that out. Test both single core and multi-core throughput. It can be very, very different. Also test if things can't be compressed. How fast is it then? Because at least when I do stuff, I like just to be able to send it everything and know that it behaves reasonably well, even if it can't compress it. At least then, if it can just bail out pretty quickly, that's actually quite a nice thing. When you do it, of course, evaluate throughput. That's typically what you're looking for. Also remember decompression speed. It can be really easy to only test one side of the equation, but then when you have to read it back, if it's really, really slow, it can be quite annoying to have to deal with that. I'll show you some examples. This is very, very small, I know, but well, basically, my main point about this, try to visualize it in some way. So this is a JSON input. We have Snappy out there. We have megabytes per second up. We have the reduction. Also note the reduction is from 70-ish% to 90, so you're not looking at the full scale. That can be important because sometimes you're wasting a lot of CPU for basically no improvement. We have Snappy out there, around 800 megabytes a second. We have LC4, around 3 gigabytes a second. We have S2, then we have the gzip down there, and then we have C standard all the way to the left. Do remember that even though you're here, you're still at around 700 or 800 megabytes per second. So even though they're fairly down low, then it's actually pretty usable still in many scenarios. Just to show that it's important that you use different. This is some binary serialized data. I think it's message pack. It could be protobuf. It could be basically anything. But you have different distribution. You have S2 way over here, and you have a big clump of stuff down there. You have Snappy still not being really super great. So you're of course looking at the highest throughput at a given compression ratio. So that's why Snappy is not really super interesting, because there's things that are better in both aspects, both speed and compression. Final example that I was a bit surprised by. So down here we have all the gzip stuff, and then suddenly we have LC4, which is gzip, and then have S2, which is better than gzip, which is weird, but it depends so much on which data you send it, how things are performed. You've got C standard way out in front. So again, evaluate with the real data, because the picture you'll get is very, very different. Good. Let's get into some real compression schemes. So we have the group I already mentioned a few times: LC4, Snappy, and S2. They're pure LC77 compressors. There's no entropy encoding. So if you have random but base 64 encoded data, you'll probably not get any compression, because it doesn't do any entropy compression and try to reduce the actual input. But because it's only looking for matches, which in random data is not gonna be there. So LC4 just got parallel compression. It's not in master yet, but I've been. It was included in the benchmark because just to be fair to it. So yeah, LC4 is definitely better than Snappy now. It's way more flexible. Then I'll get to S2, which is my own little experiment for my company. We needed a replacement for Snappy, or we would at least try to get something better. So we made a backwards compatible version of it that has concurrent compression, but also does some small things. It adds repeat matches, the repeat offsets thing, and also bigger blocks. It does tries to find longer matches, small changes. But yeah, it's made for basically the best throughput you can get and go, which I think we pretty much achieved. Though LC4, to be fair, is also, with its newest changes, definitely getting up there. One you probably know, deflate, which is used in zip, gzip, and clip. It's very old. Some would say it's from 89 or 90-ish. But it's used everywhere, right? So it's been a standard. It's been good enough for most things. The only thing is nowadays decompression speed is actually getting to be a big problem because of the way it's done. It's quite slow at decompressing, so you'll probably never get much above 200 megabytes maybe in decompression speed, which is beginning to be a problem for when you have to basically pull gigabytes and gigabytes of data through. It's not really state of the art in any way. It's done really well, but it is beginning to crack up a bit. We have bzip2. Some of you might know it. It doesn't really have a place, except that a lot of places still use it. It's not really good or the best at anything anymore. So if you can avoid it, I wouldn't use it. But hey, in some cases, it might be something that you can't decide on. And we have LCMA and LCMA2, and which is used in XC. A lot of interesting names here. So it's very good, but it hasn't really been made to be really fast. So it's probably some of the best compression, but it doesn't have any guarantees that it's fast to decompress and may take a lot of memory. There's no good Go implementation that I found. Sorry if there's one out there. So I wouldn't recommend that for anything where you can't use the command line tools in XC. Broadly is something developed by Google. We don't have a super good Go implementation. We've got one that's okay, but it's the good thing is it's in Google Chrome. So maybe if you have some static content to serve, it can help you a lot with that. My personal opinion on it is that it has too many things it wants to do. So it seems like it's a very complex thing to get into, but it may be just me that's a bit weird on that. Then we have C standard. As you may have picked up, I think this is a really good replacement for deflate, gzip, and stuff. It has very fast decompression. It's open source, well supported, and it offers quite good flexibility. So you can, okay, I want fast compression, or I want really good compression. You got pretty much a nice set of options available for you. Obviously, since I wrote the Go version of this, I also have a little stake in this. But yeah, one of the things looking at is compression across several cores. That would be interesting thing to have. So maybe take a look if that's what you're looking for. So absolute speed, LT7, S2, C standard, compatibility, gzip, of course, it's everywhere, right? LC4 is also quite well used. If you want to be able to seek in your input, there's some. You have S2, which doesn't have to decompress for you to skip forward. That's a plus. But then you also have some indexed formats that requires to be able to seek in the input. So it's placed on a file system, something like that. Web content, well, that's because that's what the browsers support. Then there's specialized stuff that only does integers, for instance. There's a lot of these, and I'm not gonna go into these because they're not that interesting. But yeah, for everything else, try C standard, see if it works for you. And yeah, that's pretty much got some links for you. You can check out, and yeah, basically the things I've been mentioning here. The slides are on the website. So yeah, that's about it. Do you have questions?
Questions?
It's my third time today I'm asking the questions. My main question will be, is there any practical point of compressing small buckets? For example, most of the time when we talk about compression, we want to compress some, well, let's say big sort of data, so for example, starting from 100 kilobytes or 1 megabyte, 30K. But what if we want to decrease the storage used by our application, but we still need the access per values? For example, we have a map of key value and we want to compress value. What will be the best strategy in that regard? For example, values are integers, floats, no strings, just integers and floats, and around 40 bytes, I think.
Yeah. Well, for if it's around 40 bytes, thing is you need to have some established state, like the dictionary I was talking about, which enables it to reference it, or where you, in terms of entropy coding, where you have a predetermined table, so you don't have, because when you decide on this, you have to include, okay, these are the symbols that we want to compress, and this is the order of them, this is how many bits each of them take up, which takes space, and that's fixed overhead, right? So if it's only, say, 40 bytes, then just the table itself is gonna eat up pretty much the 40 bytes by itself. So you definitely need some pre-shared knowledge before you can get into compressing them. But if you have a already set up encoder and you don't need to share the table between each client that reads it, then that's definitely a way that you could reduce it.
Thank you.
Sorry, Daniel. Thanks, Klaus. I was wondering, what do you think is the biggest thing holding back the Go implementation of CSTD versus the C one, in terms of benchmarks?
That's interesting, because obviously you try to match it. I think got pretty close. But well, thing is, you can write really ugly code in Go, and it will be very close to C. So I try to make it a reasonable trade-off, so the code is still sort of readable, and at least try to get close to it. One of the things that's already introduced is some level of concurrency, and that's helping it get very, very close to the C implementation. But yeah, there's obviously a little overhead in Go, specifically also because C compilers are very aggressive at inlining code, where basically when you write a constant 5 function calls up, it will inline all functions all the way up. It's very aggressive at that, and until Go gets a bit better in terms of inlining, they'll either will have really, really ugly code because we will have to copy paste the code, or as it is now in the code, if it's a really big difference, I'll inline it manually, but otherwise I'll just live with the small overhead of the function call.
Okay, along this optimization problem, are you aware about any other particular problems implementing compression algorithms in Go?
No, not problems. Do you have anything specific in mind?
Actually, for example, I know it is very often it is better to pass your values by value, not by pointer, just because Go is better, Go working better this way of passing. So this might be something like this in compression algorithms. Yeah, especially because you've got very, very small loops that have to run really, really effective, and you can't do a function call inside of that will destroy your performance. But in a lot of ways, I don't feel it's an inherent Go problem. Actually, the problems are more on a bigger scale. So making sure that you don't allocate a new encoding instance every time you have to like compress 40 kilobytes, something like that, because there's a lot of tables to set up, both hash tables and you also need the tables for the entropy compression. So that's actually a bigger issue to get around, making it easy to reuse your packages. And that has a way bigger impact because, to be honest, 20%, which is what I'm targeting in terms of matching C standard, which is super effective. It's really, really well optimized, and I try, if I can get within 20-25%, I'm really happy because that's good enough for me.
Just another one. I think you briefly touched on having AI help with the compression, and this is something that has been a lot of research around recently, I think. What do you have anything to say about the kind of learned algorithms for specific data domains?
So everything we touched on is lossless. Basically, what you put in is also what you get out. And I think that the AI can help the best in terms of where it's like JPEG, where you lose information, because it can be really good at selecting which parts are the important parts, and you can teach it to optimize for very specific visual impressions or whatever. In terms of lossless, I think the main problem is that you can set up these neural networks, but even the ones they do are extremely simple because you have to chug in megabytes and megabytes of data, so they have to be really, really small and really, really effective, and also really, really stupid because you can't have a huge neural network having to, whenever a byte comes in, it has to run through a lot of different layers and collect the output. That would simply be too slow.
Anyone else? No? Thank you.